Okay, this is section 3.1. We're going to talk about complex numbers, and we haven't defined what that means yet, but we will get to that in just a minute. I want to start out by just kind of having these evolve naturally. This first equation at the top of the page says to solve x squared plus 9. So let's just use our algebra skills that we've been using so far this semester. To solve that, we'd subtract 9 from both sides, which leaves us with x squared equals negative 9. And so far in this class, we would get to that point and we'd say, well, no real numbers. There's no real number that you can take times itself and get a negative 9. But this is where the definition of imaginary numbers comes from. We want to be able to work with that. And there's actually applications that by defining the square root of negative numbers, like negative 9, we can actually work some problems that, real situation problems that this mathematics works for. So we want to define that square root of negative 9, and that's where the imaginary number, the I, comes from. That's our basic unit for imaginary numbers is I. So there's two different ways you can write this. You can say I equals the square root of negative 1. You can also write the definition by squaring both sides and say I squared equals negative 1. So this is a whole new number we haven't talked about before. And if you were asked to find a real number whose square root was negative 1, there isn't one. There's an imaginary number. So let's go back up here to our problem. X squared equals negative 9. The way we would go from here is we would break that negative 1 off and say this is negative 1 and 9. We can take the square root of both of those now. Square root of negative 1 is I, and the square root of 9 is 3. So the answer to the problem, what is the square root of negative 9? It's 3i. And we typically put that I after the whole, or the real number. So when you do end up with an answer that has a real number times I, you put the real number first instead of the I. Okay, so let's work some problems. Square root of negative 4. Well, that's very similar to the square root of negative 9. We need to break that negative 1 away from the 4. Square root of 4 is 2, and we're left with the square root of negative 1, which is I. So square root of negative 4, 2i. Okay, how about the square root of 15? Well, the problem with this is the square root of 15 is not a whole number. So if we're asked to do this exact, and without them saying this needs to be an exact number, I would assume it does. The 15 is not a perfect square. It also is not a multiple of perfect square. You can't pull part of it out. So this, the square root of 15 cannot be simplified, so it stays under the square root, but we will pull that I out, and we typically put the I in front of a square root. I tend to put I in front, or any numbers in front of square root. I think our textbook actually does put the I at the end. So be watching for that as you do my math lab. It might require that you put the I at the end. The reason I always learn to put any number that is with a square root in front of it is just to avoid any confusion. Sometimes it's kind of hard when you're working a problem out on paper. And if I was grading your work, it's kind of hard to tell sometimes whether that I is under the square root or not. So I prefer this, but I think Math Lab might like you to write them this way. Okay, next one, square root of negative 125. So we first, we know we're going to pull an I out, right? We know that. Now let's look at the 125. And this is something that's come up a few times on problems. We've had to do these before. It was kind of something that was assumed to be reviewed, so we haven't talked about it in class, but several of you have asked about it, so we've worked through it during the office hours. Anytime you are asked to take the square root of something that you're not sure, the 15 was a small enough number, you can kind of go through your perfect squares and go, okay, 4 doesn't go into it, 9 doesn't go into it, 16 doesn't, and I'm already bigger than it, so I'm done. 125 is one of those bigger numbers, so what you do is factor it out. It actually turns out to be 5 times 5 times 5, or 5 cubed. Actually, I'm going to leave it written as 5 times 5 times 5. I think that's a little easier to follow. So I am going to rewrite the square root of 125 as the square root of 5 times 5 times 5. Well, we can break these two 5's apart and say the square root of 5 times 5, or 5 squared, is 5. And then we're left with this other 5 still under the radical. So hopefully, you know, if that came up some even before this last test and you've spent some time figuring this out, if not, we can certainly work on finding the square root of numbers, you know, not average, not estimating them using our calculator, but actually getting the calculation exact. And so then our answer is 5i square root of 5. Again, I like to put that I in front of the square root, even though I think the book, I'm not sure in this case whether they would have or not. Yeah, I think they would have put the I after the square root. Okay, let's move on. A little bit of review here. Since we're defining a new set of numbers, let's just review all of our sets of numbers so far, which is kind of everything above this line, and then we'll add the complex as a new type of number. So let's start with natural numbers. 1, 2, 3, these are basically your counting numbers. So if you ever hear me refer to natural numbers, or in the book, or as you're working problems on homework, natural numbers are the counting numbers. Add 0 in, so it's the counting numbers plus 0, you now have the whole numbers. To integers, you add the negatives of those, so you still don't have fractions or decimals or anything else. So we have our counting numbers, we have 0, and then we have the opposites of our counting numbers. Finally, we have rational numbers, and this is numbers that can be written as fractions. So it can be our whole numbers or our integers. So for example, 2 can be written as a fraction, even though we normally don't. So it is a rational number. But so is 1/2, 2/3. Even 0.75, so even though 0.75 is a decimal, not a fraction, if it can be written as a fraction, then it's a rational number. Okay, irrational numbers, these are the ones that kind of drive us crazy. That's like the square root of 125. It doesn't come out even. We're left with something under the square root, or numbers like pi, numbers that are defined but continue to have those decimals go on forever. And then also decimals that make a pattern like this. You see that pattern? 1.0300300003, and you, that ... would tell you that continues to go on forever, and that cannot be written as a fraction. So I'm going to just write out here to the side. Oh, it does say that. Sorry, I don't need to write it. It's already there. Can't be represented, instead of written, can't be represented as a fraction of integers. Okay, now we're adding our complex numbers. Complex numbers, a plus bi, where a and b are real numbers, but we've got this I. So the I is what makes it complex. The a is called the real part because we can't combine. If we end up with an answer, we have 3 plus 7i, we can't add those together because of that I. And so the 3, the number that doesn't have the I with it, is the real part. The part that has the I, the bi, is the imaginary part. And just keep in mind that a or b could be 0. So if a was 0, then your imaginary or your complex number would just be bi. If b was equal to 0, then your complex number would just be a. Okay. Now, if the a is, or I'm sorry, if the b is 0, you no longer have an imaginary number. It's still complex, but it's not imaginary. Imaginary has to have an imaginary part. Okay, let's do a little arithmetic with complex numbers. Adding and subtracting is pretty straightforward. When you're adding two complex numbers, you're going to add the real parts together, and you're going to add the imaginary parts together. You can't combine the two. So this first problem, we're just adding this complex number, 4 minus 9a. Just for review, the real part of this first complex number is 4, and the imaginary part is 9. And so we can add these together. Since we're just adding, we can basically just ignore the ignore the parentheses. You can think of it as you're distributing a +1 across the parentheses. Well, that doesn't change anything. So now I just combine like terms. 4 plus 1 is 5, and negative 9i plus 3i is negative 6i. Okay, this one is subtraction, so I do need to distribute a negative sign, or -1, across the parentheses. -1 times 1 is -1. -1 times positive 3i is negative 3i. Combine like terms again, I get 4 minus 1, which is 3. Negative 6 minus 3 more is negative 12i. So adding, subtracting, pretty straightforward. Multiplying, a little bit trickier. So before we actually do some multiplication problems on the next page, let's just talk about go back to our definition of I squared, because this is going to come into play. On the very first page, we defined I as the square root of -1. We also said I squared is equal to -1. So when we're multiplying something like 2i times 3i, you can treat it kind of like a variable. You would multiply the 2 times 3, and then you take I times I, which would be I squared. Well, we're not done, because I squared is actually defined to be -1. So this is the same thing as 6 times -1, or -6. Okay, here's another way of writing that same problem. Square root of -4. Square root of 4 is 2. Square root of -1 is I. So this is the same thing as 2i times 3i. And we just worked through this, so I'm just going to go straight to -6. So these are same thing. This has already simplified the square roots. This is with the square roots still in it. With real numbers, this is an important concept, and we just saw this. With real numbers, you can multiply before taking square roots, but not with imaginary numbers. So if we were doing a problem that just had real numbers, square root of 4 times the square root of 9, you can either take the square root of 4 times the square root of 9, which is 2 times 3, and say 6, or you can take, keep it all under the square root and say 4 times 9 is 6, or 36. I got ahead of myself. 4 times 9 is 36, so the square root of that is 6. And you see how you got the same answer? If both numbers under square roots are real, you can do that. You can multiply before you apply the square root, or you can apply the square roots and then multiply. But you cannot do it here, because if we multiplied underneath the square roots first, we would get the square root of -4 times -9, which is 36, which is 6, but our answer should be -6. So this is not what you want to do. You want to evaluate the square roots before you multiply. Okay. Let's go ahead and do a little bit of multiplication. Okay, first one is just taking, and this is just distribute. So if you're comfortable with distributing, this is probably going to just be kind of like, why are we even doing this? We're taking the 2 times 2, which is 4, and 2 times the -i, so we get -2i. Okay, pretty straightforward. Just think of it as distributing. And even when you're multiplying two complex numbers, you can think of it as multiplying polynomials, or in this case would be multiplying two binomials. And how do we do that? We use the acronym FOIL. First times first, 3 times 3. Outside, 3 times -2i is -6i. Inside, 5 times 3 is a positive 15i. And then we do the L, last times last. 5i times -2i is -10i squared. Okay, we need to do some simplifying. Obviously, we can combine these two terms in the middle that are I, but we can also simplify out here, and this is why we went through that exercise on the last page, we can simplify I squared to be -1. So if we have -10 times -1, that becomes a positive 10. That's by pulling that negative out. So then we have 9 plus 10, which is 19, because this I squared is gone, so that's just the constant 10. And then we have -6i plus 15i, which is positive 9i. Okay, let's do the last one. This is actually just another FOIL problem. I'm just going to write it out. When you square something, you take it times itself. So this is just 5 minus 4i times 5 minus 4i. You have to do FOIL. If you don't do FOIL, you're going to miss a piece, unless you just happen to know the rule for taking the square of a binomial. First times first is 25. Outside is -20i. Inside, -20i. And then -4i times -4i. Positive 16i squared. I'm going to change colors. I'll change it to green. That will show up good. We're going to combine our -20i's together. And then also, we can take off the I squared. That's equal to -1, so that's going to make this a -16. So we have 25 minus 16 is 9. -20i and -20i is -40i. Okay, I'm going to stop this video here. We're at about 15 minutes. We're going to pick it back up in the next one and talk about, we've done I and I squared. We're going to talk about what if we take I cubed, I to the 4th, I to the 5th, and so on. And then we're also going to look at dividing complex numbers. That'll be on the next video.